Okay, welcome to the next video in systems programming. We're continuing with just talking about C. Here we're going to talk a bit about the data types available in C. Not all of them, but a few of them. So to start off with, we have some numeric data types. 8 is an int. 3.4 is a double, could also be a float. And then quote, single quote, H, single quote, this is the char value of H, and C basically regards it as no different from the number 104 because of the ASCII association between characters and numeric values. So let's point out that in a sense, strictly speaking, C does not even really have a string type. Rather, it has what we more technically call a string literal, right? So when you write a thing like this, that is technically called a string literal, as distinct from a string. The idea of a string is that a string typically has certain methods and operations that are defined specifically for it. You know, think of, I guess, parsing, regex kinds of things that you might do to a string concatenation or whatever. And so that's what you would call something right? If anything had that, you would call it a string. These things, right? This kind of object right here does not support all the things that you would typically expect in a string. So I guess for that reason, we call it a string literal because it is a sequence of characters, but maybe not quite the same thing as a string. Okay. Yeah, anyway, so this is a char, this is a string literal. Okay, so now we're going to move on to talking about numeric types. I'm going to address all of this rather briefly because I just know that we must get into the technical, deep details about how these various things are implemented in a more serious way later on. So at least for now, we're just going to breeze through this in a superficial way. Int is like 0, 1, 2, or -1 or -2, and so on. How exactly that gets stored in the computer is going to be the thing that we really get into later, but for now we don't need to worry too much about it. There is then also this thing called an unsigned int, which basically just does not allow for negative values. It can be 0, it can be 1, and so on, but not -1. And as far as I know, the only reason why you would want to use unsigned ints as opposed to regular ints is, well, for one thing, if you had some particular reason why you wanted to forbid negative values, like, if it ever became a negative, you'd rather the computer throw an error rather than let this unintended negative float around in your computer, possibly causing undetected errors. That's one reason why you would use maybe an unsigned int, or I think however you implement int, the ability to represent negative values puts, a certain limit on how many different ints you could possibly store. I mean, think about it, right? Ultimately, all of these things are stored as zeros and ones somehow on your physical computer, and that is a finite computer, right? We all have finite computers. There are only so many zeros and ones that can be stored in your computer, and that puts a limit on the biggest integer that you could possibly represent. Well, if you're, using a certain amount of space to tell us that the integer is negative, right? There's got to be like some little piece of data somewhere in there storing the fact that your integer is negative or positive. Well, in an unsigned int, you basically get to free up that little space of data and maybe use it for representing even more positive values. Whatever your reason for wanting to use an unsigned int, if it's some kind of, extreme try, sort of like care about representing as many numbers as you can with the given, number of bits. Or if it's because, you'd really like to just make sure that your program guarantees that the value is never negative, like maybe for sort of like just ensuring that the program is working correctly or something like that. Whatever your reason, there's an int and there's an unsigned int. Okay. Decimal values, as we've already talked about somewhat, are represented by sort of floats and doubles. And all of these things take up a certain amount of space on your computer. So let's just skip down to the table and say a char. How many bytes, does a char need in order to be able to represent all of the various char values that we might want to represent? It needs just 1 byte. Keep in mind, 1 byte is the same thing as 8 bits. I'm sure we'll, again, talk about that more deeply in a future chapter. But 1 byte is 8 bits. A bit is just a 0 or a 1. So a char takes 1 byte. A short is a signed integer, but it does, right, like it is very conservative with how much space it uses up, right? It only uses up 2 bytes, which is pretty small. A standard int, which is usually what we use unless we have some reason for using something else, takes up 4 bytes. A long depends on possibly your computer's implementation, but 4 or 8 bytes. All of these, notice, are signed integers, and the only way that they differ is just how much space do they take up. Long, which I have never used, is 8 bytes. A float takes up 4 bytes. A double takes up twice as much. Here is how you declare an unsigned integer value, if we ever need that. I think here it talks somewhat about the ways in which computers can vary about like how many bytes. I think this table is basically telling us common standard values, but I believe it is indicating here that different computers can, in principle, use up different amounts of space for a C program and the types in a C program. So if you want to know, right, if you actually want to know on your own computer how much space does an int actually take up on your computer, you can run any program that, has this call to print, and it will, right, this is C's command. And in fact, this is, not only is this just a cute little interesting way of finding out, how big on your computer an int is, right? How many bytes it takes up. But in fact, we're going to need this function a whole lot. You're going to see probably starting in the next week or something like that of this class that we use size of all the time. But in any case, right? So you can run this line of code and find out on your own personal computer how big how much data C uses up to represent an int, and likewise with a short and any of the other types. So I guess let's leave it at that. And I guess LU in a formatted string, right? This is a string literal, and we use these little formatting commands like %. I think we saw before %f. Well, what if you want an integer value? Looks like %lu is how you take some computer object like this number and turn it into a string and put it in some place in a string. So that's how you do it in C. I think in Python that's different. I think you would say %d in a formatted string if you want an integer to go there. I think %d stands for digit, if I remember correctly, but don't hold me to that in any case. Okay, let's move on. Arithmetic operators. So this is just the ways that you can combine numeric values. I'm sure there's many more than the ones that it's going to talk about here because this is kind of a short section and I think there are lots of numeric operators. But we have add, we have subtract, multiply, divide, mod. All of these work on integers. In fact, the mod operator only works on integers. You'll get an error if you try to write either, a float to either the left or the right of it. If you use only ints, then the result is going to be an int. We've seen before that, especially with division, if one or the other side of division is say a float, then the result is going to be a float. But if both of them are integers, then it performs truncation. So like 8 divided by 3 is 2 point some decimal value. And it, because it is integer divided by integer, it just drops the decimal value and leaves only the 2. Okay. Then there's the assignment operator. Now, the assignment operator must have a variable on the left and a value, a numeric, assuming that this is a numeric variable, then it must have an appropriate numeric value on the right. So for instance, right here, assuming that x has already been declared as an integer variable, then you can compute, right, like here, it's an expression, it's not a number yet in a sense, right? 3 plus 4, not yet a number, that's really more of an expression, but that expression evaluates to an integer. And so that's fine, we can do that. And so in this code, x stores the value 7. We can use these shortcut little syntactic sugar things. So if you write x plus equals 3, this is just like in Python. It is equivalent to saying that x is going to get updated or assigned the value of the old value of x plus 3. So if x previously stored 7, then now it's going to be, this whole thing evaluates to 7 plus 3, which is 10. And so at the end of running this command, x now stores the value 10. Okay. You can increment a variable by writing that variable plus plus, that's right, for an integer value. So if variable is an integer variable, like x, say, and you write x plus plus, then whatever the old value was, it increments it up by 1. So if the old value of x was, let's say, -2, and you write x plus plus, now it holds the value -1, because it went up by 1. Okay. There are these, right, you can either write it before or after. It makes a very slight and subtle difference. Here it makes no difference. If you wrote code like this, it would make a difference. I never write code like that. So basically, as long as you write the increment on one line and then use the variable only after that command, then it makes no difference whether you write x plus plus or the other way around, plus plus x. So since I like to basically just not complicate myself, my life with ultimately not very helpful little, tricks or whatever, I just don't bother to write code like that ever. And instead, I always write it like this, and therefore the order doesn't matter, whether you write the plus plus before or after. So that's how I handle it. All right, and so I think in the next video, we'll pick up on the next section.